Next up, for assumption number 5, your dependent variable should be approximately normally distributed for each group of the independent variable. We can look at this a couple of different ways, and we want to make sure that we do it both ways. To make sure that our dependent variable is normally distributed, so we want to make sure that in each of these cases, the dependent variable follows the bell curve. First, install this package called psych. You can install it with this code, install packages psych. Then load the package psych with library psych. I've already installed the package, so I'll just load it. Next, we can look at the skewness and the kurtosis. Skewness and kurtosis are two values that tell us how tall our bell curve is and how spread out our bell curve is. We want each of these values to be within plus and minus 2 of 0, and that would tell us that our data is approximately normally distributed. In the psych package, the skew function gives us the skewness. So first up, I will run this code and save it into the skewness both groups variable. And I want to take a look at that output. Here's the output. Here we can see that we are within plus and minus 2. This is a lot less than plus 2, and this is a lot less than minus 2, so we're good with skewness. The first skewness value goes with the first column in our data, and the second skewness value here goes with the second column. Next up, we want to do the same thing with kurtosis and use kurtosi as your function and give it your data frame. Save it to this variable and then run that code, and you can see that again your kurtosis falls within the plus and minus 2. In this case, we're less than minus 1, or we're greater than minus 1. And here we're also greater than minus 2. So we're okay for now. To continue checking for normally distributed data, you also want to look at the Shapiro-Wilk test results. This is the Shapiro test code. You want to run the Shapiro test on each column or each group in your data. So here you can see that we run it on the explicit feedback group, and here you can see that we run it on the implicit feedback group. So let's run the first one and take a look at our output. Here you can see the Shapiro-Wilk normality test has been run, and it's been run on this column in our data frame. Now the important thing to look at here is the p-value. In the case of the Shapiro-Wilk normality test, for the data to be normally distributed, we should be looking for a non-significant p-value. So our p-value should be greater than 0.05. Here our p-value is greater than 0.05, so we have met the assumption for our explicit feedback group. Let's run the same code for our implicit group and look at that output. Again, we look at the p-value, and it is non-significant. So that means the data is normally distributed for the implicit feedback group. In both of these cases, with skewness and kurtosis, and with Shapiro-Wilk test of normality, we have shown that our data is approximately normally distributed for each group of the independent variable. The last assumption we'll look at is assumption number 6. This assumption says that you have homogeneity of variances. In other words, the variance is equal in each group of your independent variable. To test for this assumption, we will use Levene's test. Levene's test function is located in the package CAR, Companion to Applied Regression. Now, if you're following from previous videos, you already have installed the CAR package. If not, you can go ahead and install it with this code. I already have it installed, so I'll just run the library function to load it. Now, the rest of this code is going to be a little bit new to you, so you'll learn something here. In order to use the Levene test function, we need one vector that has all of our data in it, and we need another vector that helps us group that data. Now, we know that in this data frame, we're looking at 2 vectors, one vector for each group. This helps us understand the data, and it will help the t-statistic. It will help us obtain the t-statistic later more easily. But remember, here we just need one vector that has all of this data in it in order to use this function, Levene test. This code helps us put all of the data into one vector. How this works is we use this C, which is the vector code. So we're making a vector, and we're putting in the first column, explicit feedback, and then we're putting in the second column, implicit feedback. This creates one long column of data, and we save it to vec. So I run that code. Now you can see I have 40 elements in this one vector. And then I can look at that vector, and you can see that from beginning to end, all of our data is in one vector. So you see the first value is 5.28. And we come up here, 5.28. And the last value is 5.72025. And here's that value, 5.7025. So we've gone through the data and put everything into one vector. Next, we need one vector to tell the Levene test how to group our data. Before, our data were easy to understand and grouped in 2 separate columns. These are our groups, very simply. But now we need to think of a way to group our data that are in one long column. What we're going to do is create another sort of column. We're going to create another vector that groups our data as 1s and 2s. We're going to use number 1 to group the explicit feedback. You'll see number 1 here. And we're going to use the number 2 to group implicit feedback. So this means that, remember now, we have one long column, one long vector, and for each of these, that is the explicit feedback group, we also want a column that has a 1, 1, 1, 1, 1 in it. And for the implicit group, we want another in the same vector with the 1s whenever we come to these at the end. So at number 40, we want a 2. At number 39, we want a 2, 2, 2, 2. That way, all of the implicit group has 2's next to it. All of the explicit group has 1's next to it. This is the code in order to do that. What we're doing, you'll recognize, is creating another vector, and then we're using the function repeat. The repeat function takes the thing that you want to repeat, so we want to repeat 1 here, and we want to repeat 1 20 times. 1, 2, 3, all the way to 20, so that all of these have a 1 next to it. To do that, we can use length. So we're repeating 1, the length of this column in this data frame. And that'll automatically give us the correct number of 1's. And then we do comma, and the next element in this vector is the number 2 repeated using the repeat function, the length of the second column, the implicit feedback group. And it'll be 20 again. If this code is a little confusing, that's okay. Just type through it with your fingers, and you can always do more research about it later in order to really understand it. For now though, if you're falling behind, go ahead and pause the video and try to catch up by typing through everything. I'm going to run this code, and now we can see that we have a group, and when we look at group, you can see that this is a vector of a bunch of 1's and 2's. So if we were to put this vector next to this vector, element 1 would have a 1 next to it, and the last element, for example, would have a 2 next to it. So this is what we want. Now, in order to do the Levine test, we pass in the first vector that has our data in it, and then we pass in our grouping vector next that has our 1's and 2's, and then we put center equals mean and close it in parentheses. We want to assign this value to a variable so that we can use it later. When I run this code, you can see that I create a new variable up here, and it is called Levine statistic. And you can see that I get a warning message, but that's okay. R is helping us out. And when I look at Levine statistic and I run that code, you can see that the Levine statistic is presented here. Just like before with the normally distributed data and the Shapiro-Wilk test, we want our p-value to be greater than 0.05. And this is that value. So we can see here that this is greater than 0.05. So we have met the assumption of homogeneity of variances. So we can go ahead and move on with our test. That wraps up looking at the 6 assumptions for the independent samples t-test. Remember, this is a lot of information, and it takes a long time to learn it. You're doing a good job, getting a good start here, and over time it will start to make more sense.